Lo and behold, that gets you your 1 to 2 to 1. So that would be your correct answer. And I think most people did pretty well on that one. 83% of you answered this one correctly. Let me get rid of all of this stuff. Cut. If you're showing a recessive phenotype, the only possible genotype for you is 2 recessive genes. You have to have both of them to show the recessive phenotype. So that means you would have to be homozygous recessive. Okay. Now you can be homozygous dominant. You could have big T, and you would show the dominant genotype. But anybody who is heterozygous is going to show the dominant phenotype. Okay. And I apologize, that volume button I can't remove. That's just what shows up on my screen ever since my iPad was beaten with a screwdriver. Okay. It's
better than the Switch.
Yes, it is. I'll take it. For a dihybrid cross involving a mother who is little n, big B, so that's mama, and a father who is big N, little b. So this is where we're doing a dihybrid. We want to know how many gametes they can possibly make. Well, every egg that she makes is going to get a little n. Does it have a big N to be an option? No. Every egg that she makes is going to get a big B. Is there another option? No. So she has one type of gamete from the perspective of these 2 genes. Dad, every single sperm he makes is going to get what? Big N. There's no little n to go into a gamete. Every single sperm that he produces is going to have little b. So the answer there is 1 each. This is a real simple dihybrid Punnett square because all you have to do for this is NB. Guess what the ratio for their offspring is? It's 1 to 0. Every single one of their offspring is going to have the same genotype and the same phenotype. So there are no possibilities other than that. Okay, and the last one, which of the following monohybrid crosses would produce a 4 to 0 phenotypic or phenotype ratio? Oops. Get rid of this. Cut. Okay. So again, you could either just know this, or you can go ahead and do a Punnett square for yourself, which, you know, I'm a real visual learner. If you're a real visual learner, you may want to do the same thing. So we already know that the 2 heterozygous parents, we know that that gives you a 1 to 2 to 1 genotype, and that you've got at least one little recessive character there. So let's look at so we can rule that one out. Let's look at big H, little h. Well, that gets us... No, there are 2 different phenotypes. These 2 offspring have the dominant phenotype. These 2 offspring have the recessive. So that's not it. The only one we're left with is a cross between 2 homozygous parents, 1 homozygous dominant, 1 homozygous recessive. And what that gives us is 4 offspring who all have the exact same, both genotype and phenotype. They all have the dominant characteristic. They appear dominant, even though they're all carrying a recessive. Okay, questions, comments, or concerns on that? Okay, so how many of you want some help on the dihybrid Punnett squares? Okay, let's reteach that. So we'll go through, you have 2 of them to do on your packet. We will go through doing one together. Actually, we'll go through doing a bunch together. How's that? So what I want you to do is get out a clean sheet of paper, a blank sheet of paper. I will go through several people's examples, so they will get one done. Actually, you know what? I'll tell you what. We'll go through one example for every single individual in here. The ones that aren't yours, just copy on a blank sheet of paper. The one that is yours, you can copy in one of those squares on your packet, okay? Some of you have partner organisms, so you'll just be able to work together. Okay, so we've got our 2 parents. We've got their genotypes for 2 traits. We're using oil production and tail length. And our first task is to figure out what gametes they can produce. So, for every egg that this mother beaver produces for oil production, what alleles are capable of going into an egg here? Just oil right now. So it could be a big G, it could be a little g. She has two options for oil production. For tail length, for every egg that has a big G, what possible alleles exist for tail length? In her eggs? Just big T. So she can make two types of eggs. Okay. Now, for our father beaver, for every sperm that he creates, what alleles could possibly go in for oil production? He could make a sperm with a big G, he could make a sperm with a little g. Either one is possible. For tail length, for every sperm that has a big G, could it get a big T?
Yeah.
Yeah. Could it get a little t?
Yeah.
Yes. And for every sperm that has a little g, it could get a big T or a little t. So Dad has 1, 2, 3, 4 possible combinations of these two genes in all of his sperm. So now we're ready to actually do our Punnett square. So we'll put Mom across the top because that's just what we commonly do. So we've got GT could be in an egg, big G, little t, or little g, big T. And for Dad's contributions, we're going to put big G, big T, big G, little t, little g, big T, little g, little t. Okay. So we don't have all 16 squares filled because we don't need them. We don't have that many combinations. So now you're going to do the same thing you've always done and draw down all of those alleles. And then you're done. Okay? Now you just have to figure out all the genotypes that exist and all the phenotypes that exist. So let's go ahead and figure out the genotypes that are possible first. So when I'm listing all the genotypes, I find it easy to start off with just, okay, well there are 3 possibilities for the G's and 3 possibilities for the T's. So I just start off with listing all of them like that. Big G, little g. I'm going to need more space here. Okay, so that's all 9 possible genotypes. Now we already know off the top of our head that we don't have any that are double little t's, and I'm just going to get rid of those. So we know we don't have any of those. And, okay, the rest are possible genotypes for our offspring. So how many big G, little t's do we have? And this is where we're just going through and checking them off. So I see 1. Is that it? I think so. Big G, little t, or big T, little t. I see 1, 2. Is that it? Oh wait, no, that's not. The other one's not big G. So just 1 of that. Okay, big G, big T. I see 2 of those. Is that it? And then big G, big T, little t, I see 1, 2. And then our little g's, and this one looks actually pretty easy. I've got 1 little, big. And I've got 1 that appears to be little, big. Okay, so what's our ratio here? What's our genotype ratio? 1 to 1 to 2 to 2 to 1 to 1. Crazy. Okay, that's all you're doing. Now let's figure out our phenotypic ratio using this same information. Okay, so we're going to have 4 possible phenotypes. We've got, let's see, we have high oil with a long tail. We'll put just HO, high oil with a short tail, low oil with a long, whoops, not tongue tail, long tail. And we have, of course, low oil with a short tail. So going through this, we have to look at every single one of these. Are these individuals high oil or low? High oil, long tail. So that's 1. What about this one? High oil, long tail. That's 2. What about that one? High oil, long tail. That's 3, 4. High oil, long tail, 5, 6. And now we're into low oil. So is this one high or low? Low oil, long tail. Low oil, long tail. So we have a total here of 6 and a total of 2. So we have a 3 to 1 ratio. Nobody in this family has short tails. None of their offspring would be predicted to have a short tail. They would have some who were high oil production, a few who were low oil production, but they would all have long tails. Okay, pause. Okay, so we've got a mother and a father, maternal and paternal contributions, and the first thing we need to know is what kind of gametes can each of them make. So we'll look at mom's gametes first. Every egg she makes could get a what? Big D or little d. And every egg she makes with a big D could get what for ear size? Big E, no other options. And every egg that she makes with a little d could get what? Big E, no other options. So mom only has 2 gamete types. Okay, those are the only gametes that mom can produce, Gesundheit. Dad is a little bit more complicated. So every sperm that he produces could have what for tooth size? A big D or a little d. And every sperm that he produces that has a big D could get either big E or little e. Every sperm that he produces with a little d could get either a big E or a little e. So we have 1, 2, 3, 4 gamete types for dad. Okay? And that's the maximum. If you've got both traits are heterozygous, you end up with 4 gamete types for a dihybrid cross. Okay, so now let's go ahead and we'll set up our actual square. So we've got a square, and this one's going to be a 2 by 4 square because mom's got 2 gamete types, dad has 4. We've got mom listed across the top. We'll put dad down the side, and dad has big E, big D, big E, big D, little e, little d, big E, little d, little e. Okay, now you're going to draw them across just like you always have. Okay, so we have all of our genotypes done. So now we just have to list and count genotypes. We're going to do our tallies. So I'm going to list all the possible genotypes here.
Wait, does the big E have to come first?
When you've got a big E and a little e, yes. The big letter comes first when you're talking about the 2 alleles for one trait. Okay, so I'm going to list all the genotypes. Okay, so we've got all of them listed, and once again we notice immediately we don't have any of these that have two little e's because Mom had both big E's. So none of the offspring can have two little e's. It's just not possible. So we can immediately get rid of all the things that have two little e's. Whoops. And so we're left with these for our possible genotypes. Okay, so it's down to counting. Big D, Big E. I see one. Anybody else see any others? I don't think there are any others. Big D, Big E, little e. I see one. Two of that one. We've got it there and there. Gee, what do you know? Two of that one. One and one. Does that 1 to 1 to 2 to 2 to 1 to 1 look familiar? Why, by golly, it's the same thing we got over here. You notice that this is also a 2 by 4, so it's also one where we've got a parent that is heterozygous for one trait and homozygous for the other. So we start to see these patterns where anytime we can sort of predict. And when you do enough of these, you kind of you look at it and you go, oh, that's going to be 1 to 1 to 2 to 2 to 1 to 1. Oh, yeah. So would anybody care to take a guess what our phenotype ratios for this will be? 6 to 2. Let's go ahead and count it to make sure that we're correct. So what do we have here? We have big teeth. And what's big E's or big ears? Pardon? It's ear size? Okay. Big teeth, big ears. Big teeth, small ears. Small teeth, big ears. Small teeth, small ears. Okay, how many big teeth and big ears? Well, that's a big teeth, big ears. That's a big teeth, big ears. So's that, so's that. Huh, 6. What do you know? What are these? Small teeth, big ears. And these are also small teeth, big ears. Look at that, 6 to 2. So you start to see these, it's 3 to 1. Basically, for every 3 of their offspring that have big teeth and big ears, you expect to see roughly 1 offspring who has small teeth and big ears. Okay? Is this starting to feel clearer? Okay, we'll do one more together and then I'm going to turn you loose and I'm going to circulate. Okay, so we've got another pair here with their genotypes. And we're doing fur color and claw size. So the first step is to do what? Figure out what kind of gametes they can make. So for Mom, every egg that she produces is going to have what allele for fur color? Little h. And every egg that she produces will have what allele for claw size? Little l. Guess how many egg types she has? A whopping 1. That's pretty easy. All her eggs are going to be the same because she is homozygous for both those traits. Now for Dad, okay, so that's Mom's eggs. For Dad's sperm, every sperm that he produces for fur color could have which alleles? Yeah, there are 2 possibilities here, big H, little h. Now every sperm that he produces that has a big H could have what alleles for claw size? Little l, that's it. And for every sperm that he produces that has a little h could have what allele for claw size? Little l. So he's got 2 possible gamete types. So this is a 2 by 1 Punnett square. It's a dihybrid, but we don't need all 16 of those squares. This is not a 4 by 4. Yes, this couldn't be a whole lot easier. It's a 1 by 2. Okay, so draw them down just like you always have. Wow, that was fast. We're done. So what are the possible genotypes here? Well, if we're gonna be really precise about this, if we're gonna be really careful, well, geez, we've got all 16, right? So we listed all 9 of them, but there are only 2 that we actually have any of, and it's one of these, one of those. So it's a 1-to-1 ratio of heterozygous, homozygous recessive, and homozygous recessive on both traits. That's pretty easy. Now, what about the phenotype ratios? How many possible phenotypes do we have overall? So, in the world of all possibilities, we could have brown fur, long claws, brown fur, short claws, blonde with long claws, blonde with short claws. So, how many brown fur long claws do we have? 0. We don't have anybody with long claws. How many brown fur short claws do we have? 1. Brown or blonde fur short claws? 1. So our phenotype ratio and genotype ratio are the same. They're both 1-to-1. And what this means, now, a word about ratios. Does that mean that they will have 2 babies, one of whom will have brown fur, one of whom will have blonde fur? No. If we look at sex, for instance, biological sex, how many of you are from families of more than one offspring? How many of you have a sibling? Okay. How many of you have 2 siblings? There are 2 of you. You have 1 sibling. There are 2 of you. Okay. And every single one of you who is from a family of 2 siblings has an opposite sex sibling, right? Because if there are 2 of you, it must be 1 boy, 1 girl, right? Because it's a 50-50 chance. Anybody here from a family of 2 boys or 2 girls? Really? You have a brother? But you're male. It's 50-50. Doesn't that mean you should have a sister? And you're thinking, is it too late to trade? Okay, now you've got more than 1 sibling, right? Okay, so let's hold off on the more than 1 sibling families. Ben, you have 1 sibling, and it's a female, right? Okay, so you actually meet the odds. And Zach, I know you have a sister. You have 1 sibling, so it's a boy, right? Well, how's that possible? You're a girl. Tyler, you have 1 sibling, or you have more than 1? You have 2. Okay, we're not talking to you yet. You have 1 sibling? 2 siblings. Oh, you have 2 siblings. Okay. Do you have just 1 sibling? I'm looking for families of 2 here. Okay. No other families of 2? Tomas, do you have a sibling? You have 4. Okay, we're not talking to you yet either. Brock, siblings? You have 2 also. Wow, lots of people who are above the national average. Okay. So the fact that the odds are 50-50 or the ratios are 1-to-1 doesn't mean it works out that way. Which is why we can have families with 2 girls or 2 boys. It's why it's not always an even split. So the odds for each of their children, it's a 50% chance that any one of their children will have blonde fur or brown fur, any one of their offspring. It doesn't mean that it actually works out that way. For every individual, the odds are 50-50 at conception. So same for male-female splits. Okay, your dihybrid crosses, your whole Punnett square packet is due tomorrow when you walk in.